Spatial data modeling. Objectives. In this chapter, we will understand about the theoretical framework of GIS, accuracy in GIS, data exploration, thematic layering, categories in GIS, spatial data modeling. Theoretical framework of a GIS. Raw data is collected from the real world, and that data with its geographic positions is fed into a GIS software for data manipulation and required data analysis, and the output is gathered after analysis through that application software. This is theoretical framework of a GIS. Accuracy in a GIS. Engineers and surveyors always give more emphasis to the accuracy of a GIS. For other people like planner, rescue squad, firemen and security personnel are having less care about accuracy. To develop an accurate GIS, the required georeferences have to be professionally surveyed and located, and then carefully described in the computer form. Unfortunately, the usual geographic information system are not done completely in this fashion, and various shortcuts are taken. The usual practice is that the data on the existing maps that comes under the area of interest are converted to digital form and adjusted to the coordinate system being used. Such values will often be short on accuracy. When a map is digitized for a particular GIS application, the accuracy of the map which is digitized will define the accuracy of that GIS application. The figure shows the transformation based view of a GIS operation. But when the control stations are set up at various points of land that have been previously located in that area and surveyed with a good degree of accuracy, and then those values are taken for calibrating the digitized maps, then that GIS will achieve a good level of accuracy. The different parcels of land will have to be shrunk, stretched, wrapped or bent to make them fit with control point values. Data exploration. Data exploration is a data centered query and analysis. Data exploration can be a GIS operation by itself or a predecessor to formal data analysis. Data query allows the user to explore the general trends in the data, to take a close look at data subset and to focus on relationship between the data sets. The purpose of the data exploration is to understand the data better, to formulate research questions and hypotheses. An important component of effective data exploration consists of interactive and dynamically linked visual tools, includes maps, graphs and tables. By using a map or a table, a GIS user can perform data query. A GIS user can view both the spatial and attribute components of the data subset. For example, whenever a data has been given, the data might have large number of values and large number of thematic layering can be done. These all can be integrated and a new data set can be improved. Thematic layering. A GIS is a computer based system used to store and manipulate information about geographic features. The real world entities are so complex that they should be classified into object classes with some similarity through thematic data modeling in a spatial database. Attributes are often termed thematic data or non-spatial data, which are linked with spatial data or geometric data. An attribute has a defined characteristic of an entity in the real world. A GIS, the relevant information for a particular area can be called on the computer screen. The system can further be used to call up maps with the needed data displayed graphically. For example, you have a data or a map which is having large amount of trees, roads, railways, river is being present in that region. So, whenever in this GIS application, if you want to know how the drainage system is being located in that area, or you want to know how the transportation network is in the area, by simple query typing the network of the area, you will get the map from the GIS system. Furthermore, all or parts of data from various maps can be overlaid, enabling users to examine different sets of data simultaneously. Figure shows a few of the typical items that might be digitally stored for a particular piece of land. The items are really not layered within the computer as shown, but this type of figure is commonly used to list the type of data that are stored. The term thematic layering is used in relation to GIS, where the word thematic means relating to or consisting of a theme or themes. Categories of GIS. In the case of geo-referenced entities in a GIS, if the entity is represented by an x coordinate and y coordinate, it is said to be called two-dimensional GIS. When a two-dimensional x and y geometry integrates the third dimension z coordinate for the height parameter, as in the case of digital terrain model DTM, it is called a 2.5 dimensional GIS. Also, when the two-dimensional x y geometry integrates any other predefined simple equation for an attribute like soil type, as in the equation z is equal to f in brackets x and y, it is called as 2.5 dimensional GIS. In a 3-dimensional GIS, for the same pair of x and y coordinate, a number of spatial location points with a different z coordinates could exist, as the z coordinates are calculated independently from the xy pair. The 4-dimensional GIS or the temporal GIS is the fourth category of GIS, in which the fourth dimension represents time. Topology. Topology is a term used to describe the geometric characteristics of objects which do not change under transformations such as stretching and bending and are independent of any coordinate system. The topological character of an object is also independent of a scale of measurement. Topology relates to spatial data and consists 3 elements such as connectivity, containment and adjacency. The adjacency and containment describe the geometric relationship that exists between area feature. Areas sharing a common boundary can be defined by adjacency. Containment is an extension of the adjacency theme and describes area features contained within another area. Features such as an inland lake. Connectivity is a geometric property used to define the linkages between line features such as roads connected to form road network. Spatial data modeling. Spatial data models begin with a conceptualization, a view of real world phenomena or entities. Consider a road map suitable for use of a statewide or provincial level. This map is based on conceptualization that define roads as lines. These lines connect cities and towns that are shown as descript points or polygons on a map. Road properties may include only the road type. Example, a limited access interstate, state highway, country road or some other type of road. The roads have width represented by drawing symbol on the map. However, this width when scaled may not represent the true road width. This conceptualization identifies each road as linear feature that fits into a small number of categories. All state highways are represented by the same type of line, even though the state highways may vary. Some may be paved with concrete, others with bitumen, some may have width shoulders, others not, or dividing barriers of concrete versus a broad vegetated median. We realize these differences can exist with this conceptualization. There are two conceptualizations used for digital spatial data. The first conceptualization defines discrete objects using vector data model. Vector data models use discrete elements such as points, lines and polygons to represent the geometry of real world entities. A farm field, a road, a wetland, cities and census tracts are examples of discrete entities that may be represented by discrete objects. Points are used to define locations of small objects such as wells, buildings or ponds. Lines may be used to represent linear objects, example rivers or roads, or to identify the boundary between what is a part of the object or what is not part of the object. We may map land cover for a region of interest and we categorize discrete areas for a uniform land cover type. A forest may be share an edge with a pasture and this boundary is represented by lines. The boundaries between polygons may not be discrete on the ground. For example, a forest edge may grade into a mix of trees and grasses, then to a pasture. However, in the vector conceptualization, a line between two land covers types will be drawn to indicate a discrete abrupt transition between the two types. Lines and points have coordinate location, but points have no dimension and lines have no dimensions perpendicular to their direction. Area features may be defined by a closed connected set of lines. The second common conceptualization identifies and represents grid cells for a given region of interest. This conceptualization employs a raster data model. Raster cells are arrayed in a row and column pattern to provide wall-to-wall coverage of a study region. Cell values are used to represent the type and the quality of the map variables. The raster model is used most commonly with variables that may change continuously across a region. Elevation, mean temperature, slope, average rainfall, cumulative ozone exposure or soil moisture are examples of phenomena that are often represented as continuous fields. Raster representation are commonly used to represent discrete feature, for example, class maps such as vegetation or political units. Data models are at times interchangeable in that many phenomena may be represented with either the vector or raster conceptual approach. For example, elevation may be represented as a surface, continuous field or a series of lines representing contours of equal elevation, discrete object. Data may be converted from one conceptual view to another. Example, the location of a contour, the lines of equal elevation may be determined by evaluating the raster surface or a raster data layer may be derived from a set of contour lines. These conversions entail some cost both computationally and perhaps in data accuracy. The selection of a raster or vector conceptualization often depends on the type of operation to be performed. For example, slope is more easily determined when elevation is represented as a continuous field in the raster dataset. However, discrete contours are often preferred format for the printed maps. So, the discrete conceptualization of a vector data model may be preferred for this application. The best data model for a given organization or application depends on the most common operation, the experiences and the views of the GIS user, the form of available data and the influence of the data model on data quality. In addition to the two main data models, there are other data models that may be described as variants, hybrids or special forms by some GIS users and as different families of data models by others. A triangulated irregular network tin is an example of such data model. This model is most often used to represent surfaces such as elevations through a combination of point, line and area features. Many consider this a special, admitted, well developed type of vector data model. Variants or other representation related to raster data model also exist. We choose two broad categories for clarify in an introductory text and introduce variants as appropriate later in this and other chapters. Data and file structures. Binary number. No matter what spatial data model is used, the concepts must be translated into a set of numbers stored on a computer. All information stored on a computer in a digital format may be represented as a series of zeros and ones. These data are often referred to as stored in binary format because each digit may contain one of two values, 0 or 1. Binary numbers are in a base of 2. So, each successive column of a number represents a power of 2. Binary numbers are also formed by representing values in columns. In a binary system, each column represents a successively higher power of 2. Each digit or a column in a binary number is called a byte, and 8 columns or bytes are called as byte. A byte is a common unit for defining data types and numbers. Example, a data file may be referred as containing 4 bytes integer numbers. This means each number represented by 4 bytes of binary data, or 8 into 4, 32 bits. Several bytes are required when representing large numbers. For example, 1 byte may be used to represent 256 different values. When a byte is used for non-negative integer numbers, then only values from 0 to 255 may be recorded. This will work when all values are below 255, but considered an elevation data level with values greater than 255. If the data are not rescaled, then more than 1 byte of storage are required for each value. 2 bytes will store a number greater than 65,500. Terrestrial elevation measured in feet or meters are all below this value. So, 2 bytes of data are often used to store elevation data. Real numbers such as 12.19 or 865.3 typically require more bytes and are effectively split. Example, 2 bytes for the whole part of the real number and 4 bytes for fractional portion. Binary numbers are often used to represent codes. Spatial and attribute data may then be represented as text or a standard code. This particular common when raster or vector data are converted for export or import among different GIS software systems. For example, ArcInfo, a widely used GIS, produces several export formats that are in text or binary format. EMRC, another popular GIS, supports binary and alphanumeric raster format. ASCII numbers. One of the most common numbers coding scheme uses ASCII designators. ASCII stands for American Standard Code for Information Interchange. ASCII is a standardized widespread data format that uses 7 bits or the number 0 through 126 to represent text or other characteristics. An extended ASCII or ANSI scheme uses these same codes plus an extra binary bit to represent numbers between 127 and 255. These codes are then used in many programs including GIS, particularly for data export and exchange. ASCII codes allows us to easily and uniformly represent alphanumeric characters such as letters, punctuation, other characters and numbers. ASCII converts binary numbers to alphanumeric characters through an index. Each alphanumeric character corresponds to a specific number between 0 and 255, which allows any sequence of characters to be represented by a number. 1 byte is required to represent each character in extended ASCII coding. So, ASCII data sets are typically much larger than binary data set. Geographic data in a GIS may use a combination of binary and ASCII data stored in files. Binary data are typically used for coordinate information, and ASCII or other codes may be used for attribute data. Pointers. Pointers files may be linked by file pointers or other structure. A pointer is an address or index that connects one file location to another. Pointers are a common way to organize information within and across multiple files. Pointers are used to link the set of lines that form each polygon. There is a pointer from each line to a successive string of lines that form a polygon. Pointers help by organizing data in such a way as to improve access speed. Unorganized data would require time-consuming searches each time a polygon boundary was to be identified. Pointers also allow efficient use of storage space. In our example, each line segment is stored only once. Several polygons may point to a line segment, as it is typically much more space efficient to add pointers than to duplicate the line segment. Data compression. Data compression is common in GIS. Compressions are based on algorithms that reduce the size of the computer file while maintaining the information contained in the file. Compression algorithms may be lossless in that all information is maintained during compression, or lossy in that some information is lost. A lossless compression algorithm will produce an exact copy when it is applied and then appropriate decompression algorithm applied. A lossy algorithm will alter the data when it is applied and the appropriate decompression algorithm applied. Lossy algorithms are most often used with image data and uncommonly applied to thematic spatial data. Data compression is most often applied to discrete raster data, for example, when representing polygon or an area information in a raster GIS. There are redundant data elements in raster representation of large homogeneous area. Each raster cell within a homogeneous area will have the same code as most of all the adjacent cells. Data compression algorithm remove much of this redundancy. Summary. The spatial data modeling helps in the detailing of data into different formats where it can be used, remodified according to the requirement of the user. Spatial data modeling enables the data structure to be formatted in required maps. This spatial data modeling can be different types like raster data model, vector data model, attribute data model, which will be discussed in further chapters.